Good afternoon. My name is Ioana Doran, and I will be talking about new Rydberg series extrapolation methods based on the Stark effect in H2. So the outline of my talk is as follows. I will start with the background and motivation for this project, followed by the introduction of the Stark effect in high Rydberg states of para H2. Then I will present to you the results of the two main types of measurements that we performed. So we have millimeter waves and the laser spectroscopy. And I will finish with an outlook for the determination of the fundamental vibrational interval of H2. So molecular hydrogen is the simplest molecular four-body system. And so this makes it ideal for benchmarking ab initio calculations. You've seen this plot or something similar to this today. So you can see the potential energy curves for molecular hydrogen and for the molecular hydrogen ion. And you see that I marked the most two relevant quantities that we are interested in. So these are the ionization energy and the dissociation energy of molecular hydrogen. And these are then closely linked by a thermodynamical cycle where we have the dissociation energy of the molecular hydrogen ion and the ionization energy of the hydrogen atom, which to our accuracy goals are essentially constant. So these are known to kilohertz accuracy. So as mentioned before, briefly, our strategy is to determine the ionization energy and then to link it to the dissociation energy. And the way we do this is by expressing it as the limit of a discrete Rydberg series, which I showed to you on the right-hand side. And here you can see the different Rydberg levels denoted by n, the principal quantum number. And so their energy increases and then tends to the ionization continuum when n is infinity. So now I will briefly describe how we can calculate these energy levels in molecules. And for this, I will start with the simplest image. So this is the hydrogen atom. Here, the potential is purely Coulombic. So then by solving the radial Schrödinger equation, we can express the energies of the Rydberg levels as depending of 1 over n squared. As mentioned before, when we extend this picture to other atoms, the situation gets a bit more complicated because now the potential is not purely Coulombic. So the ion core has several protons and electrons left there. And so as the Rydberg electron approaches the core, so this goes with L, the orbital angular momentum. As L decreases and the Rydberg electron penetrates more into the core, it will feel a significant deviation from the Coulomb potential. And this we explain by introducing this set of parameters, which I denote here by mu L, the quantum defects. If we now move on to the description of molecules, there are some additional complications, such as the presence of nuclear and electron spins or the interaction between different raw vibrational channels. And so this was already explained in the talk from Maximilian Bayer from earlier today. But so very briefly, the way we determine these energy levels is by using MQDT, multi-channel quantum defect theory. So we start from low n Born-Oppenheimer curves or polarization models. We do a frame transformation, and then we are able to describe the energy levels of the Rydberg levels converging to all the raw vibrational levels of the ion. So now I will talk you through our experimental scheme. And so this has mainly two steps. So in the first step, this is the precision measurement of the transition frequency between the ground state X of molecular hydrogen and then intermediate state, which I show here as GK, but it could also be the EF state. And you've heard about this in the talk of Andres from earlier today. In Zürich, the precision measurements that we do are concerned with the transitions from the intermediate GK state to the Rydberg states. And so here I just want to stress that our excitation scheme consists of single photon transitions. So we also go from the ground state, then to another B intermediate state, to the GK state, and then to the Rydberg levels. And so here the key point is that because we always go in steps of one photon, we are limited by the delta L ±1 dipole selection rule. So in the end, the Rydberg series that we excite will always be low L states. And as we know now, their description is done by using MQDT. And currently, so in the last published result for this dissociation, for this binding energy, the uncertainty was a few hundreds of kilohertz, and this was limited by the MQDT. So the bottleneck at that point was the MQDT extrapolation, which had a 500 kilohertz uncertainty. And we've heard earlier that there are improvements in this direction. So this is now maybe just on the order of 200-300 kilohertz uncertainty. Still, in order to decrease this further, we propose an alternative strategy. And this relies on accessing the highest L states. So this will have increasingly small quantum defects that are less and less penetrating. And so this will allow us to essentially reduce the problem to a hydrogen atom problem, where the energy levels are then described by the Weimar formula. So now I will briefly introduce the Stark effect. So this is what allows us to do this procedure. And the idea of the Stark effect is that the electric field mixes states of delta L plus minus 1. And in this way, we can excite the Rydberg Stark manifold. And so what do I mean by the Rydberg Stark manifold? I show you here a calculation for the Stark map for n equals 70. On the x-axis, we have the electric field strength, and on the y-axis, the relative frequency. And so it's a relative frequency because the 0 point I reference to the 0 quantum defect position. So this is the Weimar formula for n equals 70. And you can immediately see that there are two regimes, so we can distinguish two types of states, so to say. So we have what I denote as the states with L equal 3 and 4, so these are the F and the G states. And so these, you can see that they shift quadratically, and then they merge into the other states. And this you can understand because they are degenerate, so then they have a quadratic Stark shift. In this approximation, I set the quantum defects of all states with L higher than 5 at 0. So this means that they will be degenerate. And from first order perturbation theory, we approximate the behavior of these states as linear. So we get this linear Stark manifold. So I just want to briefly mention that our calculation method here is based on the approach of Zimmermann. So this is a diagonalization of the total Hamiltonian. And the total Hamiltonian we write as the sum of the zero field Hamiltonian and the Stark operator. So on the off diagonal, we just have to evaluate this Stark interaction strengths between different states. And on the diagonal, we put the zero field energies of all the states. So for low L states with L smaller or equal to 5, we use MQDT. And for states with high L, we use values given by the polarization model. So this does not include any channel interactions. And so what are the advantages of this method? So the idea is that now we combine our transition frequencies, which we measure spectroscopically, with the Weimar formula. And so the uncertainties in the quantum defects, which we quantize in the MQDT, will have an indirect and a much smaller effect. And so this is because, of course, via the delta L plus minus 1 selection rule, all the L states will interact. But then because the effect is diluted in the linear manifold, any uncertainty in the zero field position of these low L states will be much smaller. And I will come back to this point later. Secondly, the precise minimization of residual fields, which we usually have in our zero fields measurement, is no longer necessary. So you can imagine now our procedure will be to apply a strong electric field along the Z direction. So this is the direction of our electrode stack. And this will mean that any residual perpendicular field will essentially make no difference. So in order to test the validity of our approach and the accuracy of our Stark map calculation, we started with millimeter-wave spectroscopy because this is the most accurate. So in millimeter waves, we have very narrow line widths. So this will enable us to do the most accurate comparison. So here, one needs to keep in mind that in the excitation scheme, so compared to what I showed you before, where in the last step, we went from the GK state to the F Rydberg series, now we go from a D state, so from another high-end Rydberg state. So the transition D to F is the dipole allowed transition, and we can get access to the manifold through the delta L plus minus 1 mixing as explained before. So now we need to account for the Stark shift of both the final and the initial state. So for the final state, this is the same picture as I showed you before. So we see the linear Stark manifold, and this will then be less sensitive to the low L quantum defects. However, we also have a contribution from the initial Rydberg state, because this also shifts significantly with the field. And this will then be dependent on the zero field energy of this state. And so how can we get access to some information about this initial state? Our strategy is to measure transitions to the manifold at different electric field strengths. So I show by these vertical arrows a range of field strengths where we measure transitions from this same initial state to the states in the manifold. So now these are some results. On the left-hand side, I just showed the same picture as before, but now it's zoomed in. So this is why you can see more states which shift quadratically at low field. So I include quantum defects for more states. And for reference, I showed the 70F03 state. Now I show you in red and blue markers these are the positions of the electric field where we perform measurements. And then the colors just represent the different Mn equals 0 and 1 substates. On the right-hand side, I show you a typical spectrum that we measure. So here we need to bear in mind that the axes are flipped. So compared to all the other plots in this presentation, the electric field strength is now on the y-axis, and the transition frequency is on the x-axis. So as before, you can identify the red and the blue states, and you can trace, for example, if you just focus on the red states, you can see how they become more spaced out with the field. So this is as the linear Stark manifold gets spaced out with increasing field. And so the way we can use this information is to subtract the measured transition frequencies from the very accurately, or we hope very accurately calculated final manifold positions. And this will then reconstruct the behavior of the initial state. So this I show you on the right-hand side, and you can see that the red and the blue, so the Mn equals 0 and 1 substates, both obey polynomial behavior, and they go to the same energy at 0 field, which is expected because they are degenerate in that case. So from here, we can extract some quantitative information. And this we can do by fitting this behavior of the Mn equals 0 and 1 states to a polynomial. So we find that a fourth order polynomial is enough to describe their behavior. We perform a fit where the residuals I show on the left-hand side, and these are on the order of 50 kilohertz. And from here, by doing a combined fit for these two substates, we can get the 0 field energies of the initial D states. And this we can get to 30 kilohertz accuracy. So this then validates our procedure and shows us that our calculation for the manifold is accurate, and we can use it further. We managed to get the accuracy of the binding energies of these D states with 30 kilohertz. However, now if we want to use these values further, we need to connect to the NF state. So these are what we usually use in our extrapolations. And so some further 0 field measurements would be needed. Additionally, this method is not applicable to excited low vibrational levels. So if we want to determine fundamental vibrational intervals, in the end, we would need to do the same thing, but starting from a D state above the first ionization threshold. And then this will interact with the continuum, leading to lifetime broadening. So these measurements would then be lifetime limited. So we would not be able to do this. So as an alternative, I will now move on and present the second type of measurements that we performed. So these are laser spectroscopy measurements. So I will start with describing the method for V plus equals 0. So this is the ground vibrational state. And here we go back to the initial excitation scheme. So in the last step, we go from the GK state to a final Rydberg state. And here, this GK state, we can approximate as having a principal quantum number around 3. So this means that its shift with the field will essentially be negligible. And so this removes the complication that we just saw in the millimeter waves, that we need to account for the shift of the initial state, and we might not know it accurately. So the goal would be then to determine the GK02 binding energy using 0 quantum defect positions. So this Balmer formula instead of the MQDT. So we tried to do this in the lab, and we could see this is an example of a spectrum that we observed. So in red, I show you the experimental spectrum, and in black it is our simulation. And so we can see the entire Stark manifold, which I showed you before. So here for the simulation, I need to mention that I used for the positions of the lines the results of our Stark map calculation. And for the intensities, I just used the square of the F coefficient. So this is because we go from the outer well of the GK state, which has a D character. We can go to P or F Rydberg states. However, the transition to the P states are much weaker. So then to a good approximation, the intensity is just given by the square of the F coefficient. Good. So now I told you before that the effect of the 0 field position of these low L states will be much smaller than before by using the Stark effect. And so now we need to quantify exactly how much smaller this will be. And for this, we perform a sensitivity analysis. So this means that we shift the 0 field position of low L states by 1 megahertz at 0 field, and then we see what kind of effect this has on the manifold. So here the result is that the error is reduced by a factor of more than 30. So the calculated positions of the lines in the manifold shift much less with the 1 megahertz shift in the initial zero field position of the lower states. So this allows us then to put a bound on the precision that we need in the lower states positions by choosing an accuracy which we want for the manifold, which here I put to 100 kilohertz. So then this gives us a value of 5 megahertz of precision that we need for the lower states zero field positions. And so this is usually given by the MQTT. However, in our millimeter wave analysis, we saw that in some cases, especially for the D states, which are less accurately described by the MQTT, we saw variations or discrepancies between the experiment and the theory on the order of tens of megahertz. So then in these cases, this would lead to a significant error in our calculations. But what we can do is to experimentally determine these positions. And here we make use again of the Stark effect, but this time in a small field range. So this is why you see the quadratic Stark effect in case of the 70p01 state that I show in green. So this is allowed at zero field. We just needed to use more laser power. We then record the quadratic shift and we extrapolate the zero field position. We do the same thing for the D state. And so here, because this is not a formally allowed transition, the transition moment at zero field vanishes. And then as we increase the strength of the electric field, we see the lines appearing and we can extrapolate to zero. Good, so now that we accounted for these possible systematic effects, we can proceed to do the fit. And this is a weighted position fit with two parameters. And what we fit is the calculation of the Stark map. So this you can see again for the state n equals 70. And here the heat map represents the square of the F character. So this should then give the intensity of the lines in the spectrum. And so on the right-hand side, the red spectrum is the experimental one. And we can already see that there is qualitative agreement. So this dip in intensity around minus 500 megahertz compared to the zero quantum defect position. I want to stress, so this we haven't seen before in the spectra that I showed you before. And this behavior we can understand in terms of this D state at minus 600 megahertz zero field. So as this merges into the manifold lines will get D character at the expense of F. And this means that then the intensity will drop. And this is how we get this kind of intensity dip. So we do now this weighted position fit, and we have two parameters which we can vary. So these are the binding energy of the initial state. And you can imagine that the effect of this is to shift the calculated spectrum up and down. And then we have a stray electric field which we fit, which just shifts the calculation left and right until it matches the experiment. So on the right-hand side, I show you some results where the residuals are less than 1 megahertz, and we see no obvious trends in the weighted residuals. So then this procedure is validated, giving an uncertainty of the binding energy for these GK states of less than 200 kilohertz from this fit. Now there is one last step which we need to account for in order to get a final value for the GK binding energy. And this was already touched upon by my colleagues in earlier days. So we have this kind of Doppler-free frequency determination method where we intentionally induce a Doppler shift. So this we do by changing the angle between the molecular beam and the incoming beam from 90 degrees. We induce a deviation. And so this I show you as beam 1. So this will then lead to a red shifted line. We have a mirror and we reflect it. The effect will be opposite, and then we can take the average of these two transition frequencies and get a Doppler-free transition frequency. So this we do in the beginning of the day, and then we block the reflected beam, and we record the rest of the Stark map just with one beam, and at the end we reference back to the Doppler-free position. Good. So now we can take a look at the error budget. So in terms of statistical contributions, we have the fit of the Stark map, which I explained before. And then we have the uncertainty from this fit of the induced Doppler shift. And this in total accounts to around 215 kilohertz. Then in terms of systematic contributions, a first effect would be the beam alignment. So how well we can perform this procedure. And this we account to be around 200 kilohertz. However, if we perform the measurements on different days, this will then probably transfer into a statistical error. And the last contribution, the last possible systematic contribution is then from our calculation of the Stark map. So this I explained a bit before, how we bound, or we limit the effect of zero field positions of low L lines to be less than 100 kilohertz on our calculation. Additionally, what we do is we measure at different values of N, so for different states and different electric field strength. And this I already show you on the left-hand side. So in different colors and symbols, you see the different N values that we measure. And on the x-axis, I show you the electric field strength. So we can already see that there is no obvious trend with N or with the electric field. So now this puts us in a position where we can calculate our new value for this binding energy that we get. And this I reference to 0, and is the value that you see in the center of the page. The pink shaded area represents our error. So this accounts to around 60 kilohertz. And for reference, I show you the previous published value for this binding energy. So we see that we are in agreement with this value. However, we are one order of magnitude more accurate. So as you've heard before, there are also improvements on the MQDT determined value, and the new value, which is 30 kilohertz, 300 kilohertz accurate, also lies a bit lower. So everything puts together, this is in agreement with our determined value. So now I will just briefly mention the outlook that we have for the determination of the fundamental vibrational interval of H2 plus. So here, vibrational intervals in hydrogen molecular ions are interesting in general to look at because they can give us access to some fundamental constants, such as the proton to electron mass ratio. And this is already done very precisely in Hd+. However, H2+ does not have a dipole moment. And so this makes the direct vibrational spectroscopy impossible. So what one can do instead is to measure Rydberg series converging to different vibrational levels, and then connect these results in order to get a value for the fundamental vibrational interval, or for a vibrational interval. So currently the state of this is that the experimental value is limited by 2-3 megahertz in accuracy by the MQDT. So this is because the MQDT gets less accurate at higher V. And there is also a 3 megahertz discrepancy with the theory. So what we want to do is to hopefully improve the precision and also get a new value for the fundamental vibrational interval. And our proposition is to perform laser spectroscopy of Stark maps for Rydberg states converging to V plus equal 1. And so this will then hopefully give us a value for this fundamental vibrational interval to less than 200 kilohertz accuracy. So I will just show you some very preliminary results. So this is an example of a spectrum that we observed in the lab. So we can see the entire manifold. Again, in red and in black, I displayed the experiment and the simulation. We can see that we already have qualitative agreement. And then the next step would be to do a weighted position fit as before, and test different values of N and electric fields as before. And here one needs to bear in mind that there is an additional complication, and this is because the MQDT gets less accurate. This 5 megahertz accuracy that we need on the position of Lowell states will not be fulfilled. And so we need to experimentally determine the positions of all of these states. And this can be done. So we already did this for the state. So it should all work out. We need to improve the statistics. So we need to measure these kind of star maps for different states N and different electric field values. So this brings me to the end of my talk. To summarize, I showed you how we can use the Stark effect in order to access the zero quantum defect positions of Rydberg series in para H2. And specifically, I showed you for millimeter-wave spectroscopy that this allows us to obtain binding energies of ND states with accuracies below 50 kilohertz. And for laser spectroscopy, we got a new value for the binding energy of this GK intermediate state, which is one order of magnitude more accurate than the previous one. And we also showed that the method is applicable to excited low vibrational levels. So here, the next steps would be to extend this method to other low vibrational levels and also to other isotopologues or to ortho H2. So this would then involve in the first step to refine our star map calculation in order to include spins. So thank you to my research group, to our collaborators, and everyone for your attention.
Wait. Any questions, or is the audience too tired? It's so late in the afternoon.
Hi, Ioana. Thank you. Very nice talk. So I have a question for the Doppler shift compensation. How do you connect the zero Doppler shift position that you measure in the beginning of the day to the zero quantum defect position?
So, go back. Yeah, so then now the procedure we do for one field-free measurement. So this is just for a reference line. And then we assume that this Doppler shift is the same for all the lines that we measure or within our uncertainty. So then we just need to reference everything by adding, so the difference between the position of the incoming beam and the center frequency that we determine will then be added to all of our values in the end. So essentially all the frequencies that we measured are actually 20 megahertz higher. Thanks.
So we do prefer this for the para-hydrogen, of course, because we don't like hyperfine structures so much, some of us. But if you do it for auto, then you will not resolve it in StarkMap, the hyperfine structure, or how's that?
Yeah, so then this will depend on the exact hyperfine splitting. For example, we tried doing it for HD, and here there's 1 gigahertz or so, like the first hyperfine component is 1 gigahertz lower than the others. So then, for example, the manifold of the first hyperfine component, we can clearly resolve. And then for the others, they mostly overlap. So it's a bit more difficult.
Yeah, yeah.
So then we would also need to improve our calculation.
Yeah, first, thanks for the talk. It was based on the fact that Wim was talking about the auto H2, and you did it in HD. And indeed, I was going to ask, are you confident on then doing it also as topolog? But I guess you'll still be limited by the hyperfine structure. Is it
yes, so in HD, we didn't actually do a calculation of the StarkMap with spins. The calculation is just without spins, but experimentally, this is how we first observed the StarkMaps. And then a first estimate to this 200 kilohertz accuracy would be to assume that the hyperfine splitting in the ion, which we know accurately is the same as in this high Rydberg state, and to just use somehow the first manifold, which doesn't overlap with the others.
D2 would be possible, right? D2, the D2 without hyperfine, that's one.
Yeah.
It's really small. Auto would be possible, right?
Yeah.
In the measurements where you scan through the electric fields to get your different maps, do you need to know precisely what those fields are, or is it just relative?
So here, this is one of the main advantages that we have with this method. So in principle, what we usually do in our field-free measurements is to compensate for the field. So we apply a small electric field. This leads to a quadratic star shift, and then we fit a zero field position. However, here, so we also do this for the reference line, our only zero field measurement. But then for the StarkMap, one of the parameters that we fit is actually the stray field. And so this will then be included in our fit. So even if we haven't perfectly compensated for this, it will just come out of the fit. So it's not really a problem.